Good afternoon. Thank you for coming. So today I'm going to talk about our work in machine learning at Coinbase, applying kind of graph analytics and also graph-based machine learning to tackle some of the biggest problems in crypto and blockchain. So just some agenda here. But yeah, as you might be aware, blockchain data is quite massive. So we have millions, if not billions, of entities kind of interacting with one another. We have a record of them in the blockchain. So it's a very big data, right? These entities are typically pseudonymous, so kind of hard to find the identity of these entities. And also very dynamic because, yeah, the pattern of activities change over time. So given all these kind of properties of the blockchain, we have some questions that we can try to answer. Right? And then, so my current focus at Coinbase is on fraud detection. So there's a bit focus more on the fraud detection angle, but definitely it's not isolated to just fraud. So for instance, in the fraud case, yeah, so can we detect fraud real-time in the blockchain? That's one question, let's say, right? But now going outside the fraud case, so we have also these crypto-native tokens existing on the blockchain. You might have heard things like NFTs. Can we predict or estimate the value of these kind of crypto-native assets on the blockchain using just purely based on the data, right? So that's another interesting question. And then going back to the fraud angle with these tokens now, also, a lot of these tokens can be fraudulent also. Can we detect kind of which ones are fraudulent early enough so that we can protect our users from getting harmed when interacting with these kind of crypto-native assets or tokens, right? So this is interesting because also I think with the right tools and methods, we can definitely try to tackle some of these questions and get kind of high impact results, right? So that's the blockchain, and then why graph? I think because we have all these entities interacting with each other, you can kind of make connections naturally among these entities. So naturally, we can represent the blockchain data as a graph. And as you can imagine, also, it's quite big, as I mentioned, right? So millions, billions of nodes, let's say, in the graph, right? So in particular, at Coinbase, let's say, what has helped us deal with this kind of scale of the data in the blockchain in order to get just something quick is kind of this library called GraphFrames. You might be familiar already, but this is a Spark-based graph analytics library, actually available in Databricks. And one advantage is actually, because if you deal with kind of this kind of scale of graphs, right, one natural instinct is to say, I would need a graph database. So, okay. But actually with GraphFrames, you don't have to do that. Because I think with the GraphFrames, actually, you have the capability to run standard graph algorithms. And the library has the functions to do that already. So you can run it right there and there in Databricks. So you don't have to worry about the complexity of, let's say, having to deal with graph database, moving data around to the graph database, and so on and so forth. So just a quick illustration, kind of, right? It's just very simplified, but a real-world use case that's common on the blockchain, money laundering, let's say, right? So very simplified, again, just want to emphasize, but usually in this kind of money laundering, you have kind of this pattern of flow transfers. So the intention of the sender is to obfuscate the source of the funds, so it will transfer all these monies around, but at some point, it might come back to the sender, right? So there's kind of this circular pattern. How can we detect this? And so let's say, again, very simplified case, but let's say in GraphFrames, you can write code similar to what's shown here. And then when you run it, you can you can detect what kind of activities satisfy these patterns. And we can then investigate further into whether this is indeed kind of money laundering case or not. Right? So this is all this you can run already. It's kind of you don't need GraphDB again. So Databricks with the GraphFrames library you can run this, right? So now going to the more kind of again fraud angle so in fraud. One kind of characteristic in fraud is that the fraudsters are changing their behavior all the time because they want to evade detection, right? So how can we keep up with kind of this kind of changing patterns in the kind of what the fraudsters are doing, right? So, well, since I work in machine learning, I might be biased, but I think machine learning is a great tool to actually do this. And in fact, in the fraud domain, there are already successful techniques that have been applied to do fraud detection. So you might have heard things such as random forest, gradient boosting, deep learning, neural network, right? What's kind of common across all these traditional machine learning methods is that you have to come up with the features. So you have to do feature engineering, and usually this is a manual process, right? So, and what happens if your data in the form of a graph? So again, you might then, there are features from things that are kind of natural to a graph, like, for instance, like the nodes of the degree, kind of cycles, communities, structure in the graph, maybe, node kind of the hub score or centrality score of the node, so on and so forth. But this kind of process, as you can imagine, it can be quite tedious, right? And then you want to come up with a feature, evaluate. Not every feature might be useful for the actual use case, so you have to kind of repeat the process. So it's a very tedious process. And also remember that the fraud patterns also keep changing. So you might need to adapt your features over time to capture the new fraud patterns, right? So this is a big challenge for this kind of machine learning, traditional machine learning methods. You're kind of, can we do something about it? Especially when the data is in a graph. Yeah, I think it turns out that there is a solution here, what's called graph neural networks. So this is a machine learning technique or family of techniques that kind of naturally can be applied to the graph structured data to generate kind of predictions. So the way kind of it works, kind of very briefly, is that it's using what's called message passing here, right? So here's an illustration. So let's say I want to get an idea if a node address A is fraudulent. So get a score of that. In this kind of graph neural network, what happens is that actually it will pass information. So the message is information coming from its neighbors, the neighbors of node A. It will combine them all together, and including also the information available for node A, combine them together, so do some kind of aggregation here in order to get some kind of what we call embedding, so a representation that can then be used to generate, say, the prediction that you care about. So say, an indication whether the address is fraudulent or not. So this is natural in the model itself. As you can imagine, if you have to kind of manually engineer similar features to this kind of what the message passing is doing, it can be quite tricky, right? It's not obvious. So yeah, one feature of graph neural network is that it's very good at capturing local information. So information available from, let's say, neighbor 1 hop or 2 hops away. But it does tend to struggle when, let's say, the relevant information is available farther away. So kind of, let's say, can we get information from nodes 10 or plus hops away? right? So what can we do about it? So there's actually a more recent development called graph transformers, where if you're familiar, you might have heard about transformer already, but that's kind of the architecture underlying large language models. So it's using kind of this, what's called attention, right? And then using this attention applied to the kind of this graph kind of model, what it's doing is trying to pay attention to, say, relevant information in nodes that can be arbitrarily distant. So that's just very high-level idea, kind of, right, of how it works. So that's kind of, so we have a solution also now for, let's say, if the information is available farther away. So yeah, the exciting thing, so now we have both kind of GNNs and then graph transformers, both are available to help us, right, deal with kind of this graph structured data, and then help us kind of reduce the need for manual feature engineering in order to get, let's say, a very performant model, like with state-of-the-art performance, right? Okay, so now let's say the natural question is, okay, so we have all these fancy methods now. How can we actually use it in kind of a production use case? And especially, again, remember the fact that our graph is quite big, let's say a billion plus nodes, right? So this is where, let's say, one instinct may be, okay, let's try to build it ourselves kind of from scratch, right? We did some kind of analysis on this, just to try to get a rough estimate. And remember again, Coinbase, we cannot, say, assign a very big team just solely working on this problem. Let's say 20 people is like too big. So yeah, for kind of a reasonable team size for us, if we have to do it ourselves, we estimate that, let's say, at least 6 months. We need 6 months to kind of build the necessary setup, infra, and so on to do training, evaluation, and also having this model run in production, right? So, well, thanks to actually what, there is a tool now called Kumo. So we have some Kumo people here. But Kumo helps us to kind of solve this problem. So quick preview of Kumo. So Kumo allows kind of, yeah, companies like Coinbase apply the graph, advanced graph models that I mentioned before, GNNs, graph transformers, on kind of their own data. And then to get kind of the most performant model, and then remove kind of all the complexity that is needed to train and run these models, right? So with Kumo, we develop a model on the blockchain kind of graph, where in about 4 weeks, we have one machine learning engineer working on the model, and then we got a state-of-the-art model where, yeah, we see double the precision compared to a traditional machine learning model using kind of manually engineered features. So this is exciting one that we have now a capability to protect our users from losing kind of millions of dollars. Right? So that's kind of on the blockchain, right? I've mentioned the blockchain data. Most companies, I can imagine, they don't deal with blockchain, right? And so what is it for like a typical company, like this kind of methods? Actually, this is where I think you don't need to look kind of hard to find kind of graph in your data. So when you have kind of tables, relational tables, which is kind of a typical enterprise typically has that, right? When you have, these tables are joined by kind of this foreign key, primary key already, like say your customer ID, product ID, so on and so forth. When you kind of make these connections, you already have a graph, and then you can apply things like, tools like Kumo to actually, say, be able to generate kind of predictions based on the graph that's kind of in your data already, right, in the table. So and then with tools like Kumo, actually, then what the advantage that you can gain is that, again, you don't have to worry about, say, setting up the infra, data preparation, and so on. Because then, yeah, you just need to put, say, the data in the right kind of place that Kumo can pick up, and you need to define kind of the keys. So for us, we use kind of Databricks, actually, for this. And then Kumo will take the work of turning your data into a graph and run AutoML, basically, to discover what's the best model for your use case. So this is kind of already available, actually. And this is where kind of, for Coinbase, we are excited to explore more on this, where we can explore more of not just again the blockchain data, but also our users' data, because here we see the potential of, say, if you have, let's say, taking us as an example, Coinbase, our data on our user activities. And then if we can join them with kind of, okay, the on-chain behavior of these users, and then if we have some other data on kind of, let's say, trends that happen in the crypto, all this stuff, with kind of Kumo, I think it's very easy to integrate all of them together, and then treat them as a big graph, but then be able to kind of generate a model where, yeah, then you can get kind of state-of-the-art results. For instance, let's say, right, and again, outside fraud, this is, but if you have this information on our user data, then maybe with kind of this holistic big picture, we can then make specific targeted kind of recommendations, call it, for the user in terms of maybe say, what things in crypto that are relevant for them, right, meaningful for them. So I think this is all kind of, it's already available, let's say, in our data, and then in your use case, maybe something different, but say, kind of somewhat hidden. But I think with, again, the nice thing with Kumo is that, and then this kind of graph techniques is that it allows us to uncover these hidden patterns that kind of are already present in the data. So I think this is, we are excited to go in this direction. So that's all I have. Thank you, and happy to take questions.